All right, guys, welcome back. We're going to do the next lesson in our exponential equations and functions. This is more of a kind of a review lesson. This is a review of some Math 10 topics and maybe Math 20 topics on how exponentials work. So, well, the first question here, let's just talk about this one here. Here we're just doing some transformations. I just like to keep you refreshed and keep on rehashing old things, I guess, about transformations. Now, I just have to remember that when we're doing these transformations, you do have to remember to watch out for this part, because if it's not in the proper form, then we get at the wrong horizontal translation. Now, if you remember correctly, this 3 needs to be factored out. Now, there's other reasons behind that, or how this can actually work, or other ways to find out what the horizontal translation is. I was thinking about this and I'm thinking, what's a better way to describe why does this symbol always have to change? Like, we know now, because it says +4, is actually moving left 4 units. If you think of what x value would you have to put here to make this equal to 0, you have to put a -4. So that's why it's moving over to that side. The same idea up here, what would you have to do here to make this equal to 0? You still have to put a -4 in there, so that's where another way to find that. So what would make this equal to 0? Now, the other way is to think about the y. Like if you moved everything to the other side, it would follow the same pattern as well. What would make this side equal to 0? What y value would you have to put here to make this whole side equal to 0? You can't just put 0 there, because you'd add over the 6 and do all this multiplication, and then it would no longer be 0. So you think, what would keep that side 0? That's a totally different topic. Right now, we just know that it's moving down 6 units, that there's a vertical transformation about the x-axis of 5, or 3 over 5, sorry, and there's a reflection over the x-axis. And there's a horizontal stretch by a factor of 1/3, right? You remember you have to do the reciprocal of that b value, and it's moving left 4 units. So if I were to go through and I just do the quick little mapping notation here, what's happened to my x values? So I'm going to take 1/3 of all my x values. I'm going to -4 from them. All right, let me just fix that. And then I'm going to take all my y values. I'm going to times them by -3 over 5. So that's going to do the reflection and kind of squish them in a little bit. Take all my y values, and then I'm going to -6 for them. So I can figure out where this point here is going to be after I do this transformation. Then you don't necessarily have to create this equation. If you want to, you can plug all this stuff into this equation. It's going to kind of look a little bit weird, but you could do that. You can say that -3 over 5 in the front. We've got 5 to the power of x, and you remember that all of this here replaces the x, so that's going to be my new exponent. Okay. And then I got all -6 over here. So that's what the new equation would look like after I apply these transformations. You just put an a in the front, you put your b up here, and your h and k's in the right spot. Yeah. But this is my mapping notation transformation here. So what I can do now is I can put a 3 to find out what my new point is. I'm going to put 3 in here. So 1/3 of 3 is 1, -4. So 1 minus 4 is -3. And then I can do 125. So 125 times -3 over 5, which is -75, -6 is -81. There we go. So now we know where our new point is. We just use this mapping notation and these 2 points here as my x and my y. We find out what this new point is. It says here state the domain and range. So now the domain, remember all exponential functions. It doesn't matter what my x value is. It always seems to be it always works. So XER. Now my range is slightly different. Remember our original graph, the range had to be greater than 0. It couldn't be equal to 0 and it can't be negative. But since we translated this graph downwards 6 units, my range, and we haven't, oh, and we did a reflection over the x-axis. This graph is now actually pointing downwards, and it got moved downwards. So my y values have to be less than or equal to, or not equal to, sorry. Less than, because it's being reflected, -6. Okay. And the equation of the horizontal asymptote. So our asymptote is related to this transformation that got moved downwards. The reflection part doesn't change where the asymptote was because it was on the y-axis originally, or sorry, the x-axis originally. I got moved down, so my asymptote is y is equal to -6. All right. So the rest of this lesson here is going to be about just using our exponent laws and our rules that we remember from Math 10C and Math 20-1. So when you multiply and they have the same base, as long as they have the same base, if I multiply them, I can add my exponents together. If I divide them and they have the same base, I can subtract my exponents. And this is very key that you go the top minus the bottom, don't switch it around. When you multiply, it doesn't really matter. You can add them in any order. So here I got power to a power. So this is my power to power rule. Pretty simple, you just have to times them together. Anything raised to the power of 0, which we already discussed from the previous lesson, is 1. Even if it's a negative base, it's 1. But this one here, you have to be very careful. Technically, the way this is written, it should be a 1. That's what you would think it would be. But if you type that in your calculator, you actually get -1. Because this negative is kind of its own entity. It's like a -1 times b to the 0. So that's what your calculator would do, and that's what you should get. You train yourself to think too. If you put the negative outside the square, outside the exponent, it's tacked on after the fact. Now here I got the power rule, or sorry, the quotient. This is the product rule, sorry, not the quotient rule, product rule. When you multiply things and you raise them to a power, you have to multiply it or raise everything inside the brackets that same power. The same thing with the quotient rule. Now, this one here, you just have to remember that square root is the same thing as a rational exponent, where the index here, what I'm circling, this index, is the denominator of the exponent. Okay. Negative exponents, remember those ones? We dealt with those in the last lesson as well. You can change them to be positive. Remember that if it's over 1, you can also just kind of group it together and say 1 over a is equal to the power of x. All right, if it's in the denominator already, you can take the reciprocal of that and it'll just move to the top. And if it's a whole rational expression, you can change that to have a positive exponent. All right? Okay. So now we're going to use some of these rules to help us figure this out, like especially those negative exponents are going to help us. Here, the number 8, if I want to change that to be a base 2, right now it's a base 8 number, I can change that because 8 is the same as saying 2 times 2 times 2, which is the same as 2 to the power of 3. So I can change numbers to different bases. Technically change any number to any base, but most of the time we want to change it to has a nice integer exponent. And I say integer because sometimes they can be negative, like this one here. I want to change this 1 over 27-bit number here. Let's just put that in brackets. I want to change that to say some 3 to the power or something. So you have to maybe just do a little recall, like 27 is 3 to the power of 3. All right, so that's just 3 to the power of 3. Now, this is just the same as saying 1 over 3 to the power of 3. Right? Because that same rule I had before, because the 1 on the top. If you expand this out, 1 cubed to be 1, 3 cubed to be 27, it'll end up being 1 over 27 still. Now, I want it to be base 3, not base 1 over 3, so I want to do a little reciprocal. So we're going to take that, and we're going to flip it over, and by doing so, we change the exponent to be a negative exponent instead. So that's what it would be as base 3. This one has an exponent of x already, but that doesn't change anything. We just kind of treat the 64 separately of the x, and we'll deal with another exponent rule later. So 64 is 2 to the power of 6. Yeah, 2 to the power of 6. All right. And now because we have a power to the power, we can multiply our two exponents and get 2 to the power of x, or 6x. Okay. You're going to see later on why this is important when we solve exponential functions by not using logs yet. We're not going to learn how to do logs until later, but we can use these exponential changing bases in equations where we can drop our bases, and we'll see that one later on. But usually it's better if you simplify these down first. So you look at these two, 16 and 32, we want to change it to base 2. You have to recognize that these two numbers are technically two numbers that can be 2 to the power of, in this case, 2 to the power of 4 gives us 16. So that's still 2 to the power of 1/4 from before. And remember that this whole thing, I could change the square root into a rational exponent. And 32 is, oh, I was, oops, that was wrong on that one, 16. Oh yeah, this is 2 to the power of 5 here. Okay, 2 to the power of 5 is 32. So we can simplify this down. We got power to the power here, so that's 1/4 times 4, so that's just 1. And then this one here is 5 times a half, so that's 5 halves. And then we're also multiplying these two, and they both have the same base now. Up here, I couldn't do that before because the bases were different, so I can't do anything with the exponents between the two. But because the bases here are both 2, I can now add my exponents together, and I get whatever 5 over 2 plus 1 is. Math, enter, enter. Oh, so 7 over 2. There we go. If you want, you can change it into a square root again, because the denominator is 2 on my exponent, so that's a square root 2 to the power of 7. And we're just going to leave it there. Yeah, we're not going to bother multiplying that out because I want to keep it in base 2. All right, so we're going to do the same thing with this. This one has x's in the exponent, but I want to just change it to base 5. So hopefully I can change all these numbers to be in base 5, like 5 to the power of 3 is 125. So that's 3x plus 2. And then 25 is 5 to the power of 2. And then we have a negative x plus 5 there. A negative 5x, sorry. Okay. Then we're going to apply some of our rules like we had up here, over here. This is going to be the same thing. I'm just going to take the reciprocal of that and change the exponent to negative. So this turns into 5 to the power of negative 3. And then I have 3x plus 2. And this one I'm just going to apply the power of the power rule. So that's 5 to the negative 10x. Yeah. You'll do power to power, but remember when you do power to the power, you're going to multiply these, and this is technically a binomial. So you're going to do the whole distributive property here. And we're going to get 5 to the power of negative 9x minus 6. Yeah. And then this is 5 to the power of negative 10x. Okay. And because now they have the same base, we can add their exponents. So when I add my exponents together, I get 5 to the power of negative 19x, because they're both negative. So when I add them, it ends up being more negative, and then minus 6. Okay, there's my nice base 5. Can't really do too much of that. Welcome to 30-2s. I'm just jumping in here to make a little correction about F here. You probably won't see the mistake here. Hopefully I can cut this into there and it'll probably be seamless as possible. But F should be written as, if we're going to follow the same rules that we had before, if we have the same base, so these both have the same base of 3, we're going to write this as 3. And since they have the same base and you're dividing, you're going to subtract your exponents. So I'm going to take this exponent that's on the top here and minus the one that's on the bottom. Okay. Now, to simplify that, you just multiply this negative into the brackets, and you're going to get 5t minus 1 minus 2t plus 6. So you got a minus minus there. So my overall answer is going to be 3t plus 5 as your final answer for simplifying that base. Okay, back to your regular schedule programming. See ya. All right. Now there's a reason we're doing this. Like we're wanting to simplify these down so we can actually solve for something that's in the variable or in the exponent here. So here we have an x here that we're trying to solve for. We're solving for the variable. We want to know what x is equal to make these two sides equal to each other. Now you could just guess, check, and revise until it's done, but we're going to solve this the algebraic way. It says here algebraic. So guess, check, and revising is not an algebraic method, but changing the base to match is a very algebraic way. Sometimes you can't always do this, but if you can, go ahead and try it. These here 9 and 27, I already know both are to base 3. So I decided to change into both base 3. So 9 is 3 squared, and there's 2x minus 5 from the exponent originally. And 27, we found out before was 3 to the power of 3 and x minus 2. Now, we're going to simplify these two sides down here by multiplying the exponents, the power to the power. Let's go minus 5, minus 10. Okay. So now we've simplified our two expressions, our two sides here. They both had the same base. And because they both had the same base, we're allowed to what we call drop the base. And we could just look at just the exponents themselves. You got to think of the logic behind that is like, if I have like 2 to the power of 2 and the other side is 2 to the power of x, what does x have to be to make sure these two numbers end up being the same thing? Well, this has to be a 2. It's the only way that works out. Okay? So you could just say, okay, now rather than going through all the steps here, we just say, okay, because they both had the same base on each side, I can just say x equal to 2 and I'm done because I'm just looking at my exponents. So we do the same thing here. We just look at our exponents because the bases are the same. We just make our exponents equal to each other. So we just drop the base and then we just solve for x. So subtract over that 3x to the one side, gives me x by itself. And I'm going to add the 10 to this side and get 4, x equal to 4. Now, most of the time you'd want to verify your answer just to see if you did get it correct, or maybe there's an extraneous solution. When we solve these ones, they're probably not going to be extraneous solutions. But we should just verify. So I'm going to go back to my original equation here and put a 4 in the exponent on both sides. And then just solve. So this one here is going to be 27 to the power of 2. And this one here is going to be 8 minus 5. So this is 9 to the power of 3. I just want to double check now. Both sides, so 27 squared is 729. 9 to the power of 3 is also 729. So both sides were correct. So x satisfies this. Okay. So what we're going to do now is we're just solve for x. So we can do the same thing here. We have to decide what base we're going to use. Sometimes you may think, okay, how do we decide what base to use? Some of them are easy to look at. You could say over here, like, oh, I'll use a base 4. You could use a base 2. Maybe that'll work out the same for both. Down this one here, D here. You could use a base 5, maybe. It looks like something with 5s. If you can't decide what base to use, then you're going to have to, or maybe in base 2. No, not base 2 on that one. Yeah. Maybe I'll just simplify it down first too. Maybe you got to decide. So maybe pick the lower base here. So 32. That's a one I'm going to use. And I'm going to say, how do I figure this out? So maybe I'm going to go with my calculator. Go 32 to the power of something. So we're just going to guess and see if it works. So 32 to the power of 3 is too small of a number, and to the power of 4 is too large of a number. So 32 is not going to be a good base here. So then you pick another one. So 32 we know has a base 2 already. Maybe I can change it to a base 4. No, base 4 is not going to work. Maybe I'm going to have to deal with a base. I got to look at this one here. I don't know if this number is supposed to be separated from this 8. Can't remember if I changed this so that they are two separate numbers. Let me just double check my equation here. Oh yeah, they're supposed to be two separate sides here. I'm thinking this 5 to 1, 2 might be a typo, so I'm just going to erase that. Just imagine you didn't see that. All right, so look at 8 and 32 is a little bit easier to solve. So I can say this is both base 2. So I can change 8 to 2 to the power of 3, and that's going to be x there. And I can change 32 to be 2 to the power of 4, x minus 4. So here we have 2, 3x, and then if we have 2, 4x minus 16. Because the bases are the same, now we can drop our bases and then solve. So I'm going to just move the 16 to this side and the 3x to the other side, because I just like to have positive numbers. So x equal to 16. Okay, let's get rid of that 5 5212, that was there originally. These ones look like they're all not typoed on me. So 1664. So let's look at 64. You can say 64 is to the power 4 to the power of 3. So you don't have to always go to the lowest base, but you could say 16 is 4 squared. That's the same number. 64 is 4 cubed. Apply your exponent law here. So you're just going to multiply that 2 into both those numbers. Multiply this 3 into both these numbers here. And then drop our base. All right, so subtract over the 2x, minus over the 8. Oh, minus over the 3, sorry. So I get negative 11 here. So we get x is equal to negative 11 over 4. Yeah, we can get fractional exponents. That's fine too. Hopefully we can do a little verification here just to make sure this actually works. So 16, yeah, it just seems like a weird number. So we're just going to verify that. So negative 11 over 4 minus 4 is that exponent. And then over here, we're going to put negative 11 over 4 plus 1. So I'm just going to punch into my calculator with those exponents. Negative 11 over 4 minus 4. Yeah, I get a pretty ugly number there. But I just want to make sure that both sides are exactly the same. So, yeah, they both end up being a pretty small number, like 7.54 times 10 to the negative 9. It's fine, but they both end up being the same. So they work out. All right, so the process for all these are pretty much going to be the same. D has this 2 in the front here that we're going to deal with eventually. But these are going to be the same. Just watch out because this one's 1 over. Your bases have to be exactly the same to drop the bases. So you want them to both be either just whole number bases or both be fractional bases. But I can change a 36 to be, and maybe if I could best base for this be like 6, this would probably be 6 squared. So can I get, using 6, can I get 212 or 216, sorry. Yeah, 6 to the power of 3. So this is 6 to the power of 3 on this side. Okay, so that's what I'm going to do this time. I'm going to change it to a 6 because I want to do the reciprocal, and I know that 36 is 6 squared. This will end up being negative 2 here because I want to do that flippy part. And then we're going to go multiply that in. So we get 6x plus 4 on that one. And then over here we get negative 6x plus 12. Now I can drop the base. And rearranging. So I'm going to add over the 6x to this side, and subtract over the 4 to this side, divide both sides by 12, and then reduce the fraction down and get 2/3. Right. Now, if there's a number in the front, what you're going to do before, because I'm looking at this and thinking that's a base 5, that's a base, could be a base 5, but there's a 2 here. And I can't combine a base 5 and a base 2 together. So maybe a smart way is to get this piece by itself first. So let's see what happens if I divide this 2 to the other side. So if I go 1250 divided by 2, actually I'll just write that in there. I'm going to divide the 2 over, I get 625. And look at 625, that's a much nicer number when you want to do bases. So 625, that's the same thing as 5 to the power of 4. And to find these exponents out, you just kind of guess check, right? Unless you know all the exponents off by heart. And this is going to be 5 to the power of 3. I just knew that one was going to be 4. Do your power rule here. 6x minus 3, and this is 5 to the power of 4. Now we could drop our bases. 6x minus 3. We're going to add that over. And then solve for x. There we go. So it kind of works out the same way. That this one here, I can't really divide this 2 over and expect anything to happen because this is not just a number like this. This is just a number, had no exponent. So if I divide this 2 over, not going to work because the exponents are all different. And I can't multiply the 2 into the brackets because they both don't have the same exponent. If they both had a power of x, yeah, then I can combine these together. But because this is the power of 1, it doesn't really work. But I'm going to put a 1 there because that might be useful when I change everything to a different base. All right. So 32 is the power. I don't really remember that correctly. It's 32 power of 5. And this is going to be power of x here too. I'm just going to put x on the outside of that. All right. Then I can change 4 to the 2 to the power of 2, x plus 1, and then I can change the 8 to 2 to the power of 3 to the power of x. All right. So let's just simplify this down a little bit nicer. All right, and then this side over here is going to be 2. Oh, sorry. Uh-oh. Oh. 2, I'm going to multiply that into the exponents. So 2x plus 2. And this is going to be 2, 3x. All right, using our rules, because these are the same base now, I can add the exponents together. So I can say this is going to be 2x plus 3x. That's 5x plus 2. And here I can add my exponents together. You have to remember that this is an exponent of 1. So when I add these together, you get 5x plus 1. Okay. Now I can draw my bases. 5x plus 1, 5x plus 2. Oh, what's going to happen here? So I'm going to add. All right, so let's say I subtract over the 5x. I'm left with this now. And when you get this situation, what this means, because 1 does not equal 2, or if I subtracted things around, 0 can't be -1, or 0 can't be 1. You get a number equal number, and there's no more variables because I subtracted these 2 pieces out. 1 can never be 2. This doesn't work. Because if you get this situation, that means there is no solution. No solutions. Now, what that means is if I were to graph this, put all this in the y is equal to 1, put all this in the y is equal to 2, these 2 graphs would never intersect each other. There's no intersection between the 2. There's no x value here that could satisfy this equation. It'll never work. Yeah. Just sometimes that works out. Graphs will never cross each other. Maybe the 2 graphs, one's going like this, and another one's going like this, but this is going to be a little bit faster. So they'll never actually touch each other because they're spreading out faster up here, and they're reaching the same asymptote, so they'll never actually cross over each other at any point. So that happens. But that's okay. So that's the end of this video. We're going to talk about how do we solve these problems graphically. Like I was just saying, like if you top here, we can just graph the 2 and find out when they intersect each other. But that ends off this video for now. Once I finish out part B, I'll give you, or part C here as well. It's quite a bit more to go. I will give you guys a little bit of assignment to work on, practice, and then we'll move on from there to the next lesson. But I'll see you in the next video.